and welcome to the lesson on electric fields. So your goal today, I want you to be able to explain and determine forces acting on objects that exist within an electric field. So where are we starting with this? Most of this, you're just kind of paying attention to the conversation. So earlier, we discussed what the term field means. So it refers to the space surrounding a source. So we've already talked about planetary. We talked about if I have Earth, there are multiple field layers indicating different strengths of gravitational attraction and so on and so forth. Same idea, exact same idea actually, except now we're talking about electric fields. All right, so they're fields that surround charged particles. So we're looking at a force at a distance. We're looking at not having to come into contact with an object, but being able to apply a force. So electric charges, we know they attract and repel each other, and they don't have to come in contact. So the force of attraction, we already did that in an earlier lesson. It's governed by Coulomb's law. For forces such as electric fields, you can't view them very easily by the human eye. So we develop a visual system that allows us to understand and illustrate what's going on. And I've got an app that I'm going to show you, or a website that you can try on your own. I'll post the website, and I'll try to do a couple of demos and see how they record. Sometimes they don't record very nicely. So the basis of field maps and electric field lines. So these lines they represent that electrostatic force. So it's the same as the gravitational lines. But here are some of the rules when you're drawing them. So we're talking about positive. We generally start or assume we have a positive charge when we draw our field maps. So what's that mean? So our rules. The electric field lines always start and point away from any positive charge making up the field. If it was negative, it would point toward the charge. Okay, but so for positive charges, we assume they point away. All right. Second point, the number of field lines emanating from the charge is proportional to the magnitude of the charge. And remember, field lines may never cross. We did that in the grade 11 course when we did electromagnetic fields. Same thing here. Field lines cannot cross. The stronger you want the charge, the more field lines you'd better draw. Fields can be mapped out by first finding equipotential lines. So those are the lines where the force is the exact same. And these lines are points where, well, I just said that, where the lines forces are equal. Field lines are drawn perpendicular to the equipotential lines. And I'm going to illustrate that in a second here. And field maps can take on many different shapes, but there are 4 basic distributions that I'm going to go through, and we'll talk about each one. Finally, the note at the end, the electric force vectors, so the force of attraction or repulsion, are always tangential to the drawn field lines, and it's going to be demonstrated in the examples. I also have a great little lab that you're going to do that illustrates these exact electric field lines, so it's kind of neat. So you'll get an opportunity to actually see it in action. So let's talk about point charges for a second here. So I'm going to start putting some stuff. These are actually separated, all right? I'm not, these 2 points, it's actually 2 separate examples. So just sketch a line down the middle if you don't have one already. So what does a positively charged particle look like? Well, I'll draw in the equipotential lines first. So the equipotential lines are these lines here. So that is using Coulomb's law, you would feel the same amount of force at that layer. You'd feel the same amount of force at that layer, and so on and so forth. So the green here for me is your equipotential. Oh, here are equipotential lines. All right. Now, perpendicular to that, you would draw your field lines or your force lines. So just going to draw a couple in. All right, and we have them. The arrows are pointing away. And you'll notice that they are perpendicular to all of the equipotential lines throughout. So your force is always perpendicular to your equipotential lines. So that is your electric force. All right. That will be our vector. We also call these, before I forget, the black arrows, those are my field lines. All right, those are the field lines showing the direction of force. The next one, what happens if it's a negative charge? So nothing too shocking here. So I'll draw my equipotential lines in. Looks like I'll be able to fit 3. And in this case, if it's a negative charge, the convention is that the field lines point toward the charge. The more I draw, the stronger the charge is. All right. And in this case, your E pointing toward the center of the charge. Okay, so that's just the basics, how to draw for a point charge. So there are 4 basic field configurations here. So the first one is 2 equal point charges, opposite signs. So we're going to have a positive and a negative charge. So let's draw the field lines to start with. So I'll do those in blue. So positive and negative, we're going to have a field line going directly between the two. And as we move out, we are going to get some curvature because it does come out of the charge perpendicular and enter the charge perpendicular. So there's that amount of attraction. I should be actually coming in a little bit more perpendicular, like that. And for the ones they go off the page, I'm not going to bother looping them around, but they come in, come like that, and I had another one and another one coming from this way. So there we go. That's what the field will look like in general. What will the equipotential lines look like? So this is where is that electric force equivalent. So instead of a ring, so I'm going to do this in the red, here's my equipotential line. So instead of going around the charge, it's going to create kind of a figure 8 configuration. All right, and the subsequent rings kind of follow that same pattern. All right, so my red again are my equipotential lines. I'm not going to spell that out again. It's too many letters for me. So those are my equipotential lines. And the blue are the field lines. All right. So what does that tell us? Well, our force, the electric force that you were calculating, and I'm going to do these in black. I think that's the only color I really got set up for doing this properly. Okay, so black, the force that you were calculating with Coulomb's law is always tangential to the field lines. Okay, so it doesn't matter where I draw my electric force, it will be perpendicular to those field lines. Okay, so I'm just going to put that note below here in the space. So my comments, remember that. How do you calculate electric force? Well, we are simply using Coulomb's law, and Fe is always perpendicular to the field lines. Field lines. There we go. Okay, so that's all I wanted to stress there. And there we are. So those Fe, they are tangential. It means they just touch or spin off the curve. Now, in the previous lesson, and I'm just going to emphasize this magic pen, we were doing Coulomb's law directly too. So this is obviously, this is where the strongest electric force is going to be because it is closest point between the two. So that would be our Fe, and that's what you calculated in the previous homework. As you move away from that center line, then that Fe is going to point in that direction. And in a sec, when I pull up that app, it will show how a particle reacts in that environment to emphasize it. All right. The next one, what happens if our 2-point charges are the same? So I'll do positive here. So let's make them both positive. So what happens, I'm not going to bother with the equipotential, I'll just draw my field lines for now. So we have repulsion. So we have that force that starts between them, and since they repel each other, what happens is those field lines are going to go like this, and starting from the same spot, kind of push away, don't cross each other, and from that, they kind of spider out. And on this side, kind of just goes straight out. It's already emanating outward. It's just when you're in a little bit closer that they do have to curve a little bit. And we get a system or a field system that looks like that. All right. So what does that mean? Well, I'll use red here. I'm not going, like I said, I'm not going to do the potential lines. I'm not too worried about it here. If I was right here at point number 1, all right, so I'll put point 1 over here. If I was to drop a particle in there, the electric force would be 0 newtons. All right, because you're right in the middle. You're being pushed on equally from opposite directions. If I slide you up, so I'll just use a dotted line. Say I slid you up to this point right here, point 2, or equivalent, move you down to point 2. The electric force is no longer 0, so I'm just going to put not equal to 0 newtons. And what that would mean is if I dropped you in, if you were a positive particle, you would then go flying in the direction tangential to that field line. So you would have flew off that way, or you would have flew off that way at that given point. So it's just at that point of contact. All right, so there we go. Oops, and up top there, you're likely thinking, where did I get that? You want to change that to same, copied and pasted the slides, but didn't make the changes, the appropriate changes. Okay, so getting this final one in. What happens when you kind of take a step back? So now I'm going to take one step back. So earlier, inside this red box, all right, I am going to draw the red box maybe a little bit bigger here. So that red box is from a previous slide. Okay, so I'll just say see previous slide. Slide and note. So that's saying, and I'll just show you right now since you're paying attention to this, that inside that box is this picture right here. Okay, so I'm going to shrink it down inside that box. So field lines, Now, what happens as you zoom out? So we start to zoom out a little bit. So what is happening here in this system? Well, all those positive field lines, what's happening is the attraction's not strong enough to bring some of the field lines back in, and they'll continue on like that, the field lines. And as you draw more and more of those field lines from the opposite side, what happens, oops, is they start to spread out, and I'm not drawing it very well. And I'm going to show you the internet app that illustrates this much better. But because that force of attraction is not enough, what happens is that this, as you zoom out further and further, this big picture, regardless whether you have two positives, two negatives, or opposite signs, it starts to take on the image of a point charge. Okay, so at a distance, two charges, regardless, sign, that is in brackets, will take on the same properties as a point charge. So what I'm hoping for in the next video, and you'll know when you start it up, I'm hoping that I can just have the charge. I'm hoping I can have the internet app up and I can demonstrate and it records properly. Sometimes I have trouble with some of the software, and then I can make that conversation or talk about it as we step through it, and you can just watch what's happening. And then I'll put that app also on my website so you can try it on your own, just to take a look at some different options. All right, so we'll take a look at that, and hopefully in the next video. And if not, I guess in the next video you'll know that it didn't work, and you'll have to go try it on your own.